Hey everybody, Dr. A here, and in this video we're going to be exploring an example of how to compute a moment when we have a three-dimensional vector. So let's go ahead and get started. In the given information, we're being asked to compute the moment about point O, and we're being asked to do this two different ways. Part A says measure R from O to A, and part B says measure R from O to B. So let's look at the figure that we're given. Here we see we have a positive x-axis here, we have a positive y-axis here, and we have a positive z-axis here. And we're given a force vector that extends from point A to point B. The tail is at point A and the head is at point B and has a magnitude of 50 pounds. So in order to calculate this moment about point O, how do we do that? How do we get started with this? Well, let's go ahead and write solution. And we know that the moment when we have Cartesian vector notation comes from the cross product. We say R cross F. So if you notice, we have Cartesian vectors here. We need a Cartesian position vector R and a Cartesian force vector F. Okay, now how do we get these? Well, let's actually start with the Cartesian force vector F because we already know the magnitude of the vector that we have, and we know 2 points that define it. Point A is defining its tail, point B is defining its head, okay? So let's go ahead and write that down, all right? I'm going to put a comma here, and I'm going to say point A is going to be defined as 2 feet, 3 feet, and 0 feet. How do I know that? Well, again, we look at point A, it's got coordinates of positive 2 feet in the x direction, positive 3 feet in the y direction, and it's in the xy plane, so it has a 0 z value. What about point B? Well, I know point B has coordinates of 1.8 feet, 2 feet, and 2 feet. And again, how do I know that? Well, I'll look at point B here, and I look at this little projection down here, and it has an x coordinate of 1.8 feet, a y coordinate of 2 feet, and a z value of positive 2 feet. So there's my points A and B. So how do I use this information to express that force F as a Cartesian vector? Well, what I do is I say Cartesian force vector F is going to just be equal to its magnitude times the unit vector that's defining F, okay? And so then the next question becomes, how do I get this unit vector that defines that force F? That's what the subscript right there means, the unit vector defining the force F in our problem. Well, if you go back to several videos ago, we have some video material that explains to us how to do this. The unit vector F is going to be obtained by finding the position vector of F and dividing it by its own magnitude, okay? So it's the Cartesian position vector that defines that line of action of F divided by its own magnitude. Now, if I piece all this together, what will I have? Well, I'm going to say this equals, and remember, how do we get position vectors? We take the coordinates of the second point minus the coordinates of the first point for I, J, and K. So when I write this out, I'm going to write 1.8 feet minus 2 feet times I plus 2 feet minus 3 feet times J plus 2 feet minus 0 feet times K. And then I'm going to divide all of that by the magnitude of that same position vector, okay? And remember, we get magnitudes of vectors using the Pythagorean theorem, and so this will just be minus 0.2 feet squared plus negative 1 foot squared plus 2 feet squared, and then square root of all of that, okay? So again, this part we've done before in some videos prior to this. So if I punch all of this through, what do I get for that unit vector? Well, maybe pause the video and pull your calculator out and compute this with me, so make sure we get the same thing. But when I punch all this through my calculator, I get 0.0891 I minus 0.445 J plus 0.891 K. All right, so that's my unit vector that defines the line of action of that force F. So how do I get the Cartesian force F? Well, we use this relationship right here. We say the Cartesian force F is just the magnitude of F times that unit vector. So I say 50 pounds, that's the magnitude that was given to us, multiplied by each one of these components. And so when I do that, I punch that through my calculator and I should get negative 4.455 I minus 22.25 J plus 44.55 K. All right, and collectively, this Cartesian vector is going to have units of pounds. You could write the pounds inside of each of these components if you'd like as well. So that's my Cartesian force vector. And so if I want to, keep track of things, I can check off that value of F. Now, in order to get this moment that the problem is asking for, I need a position vector. Now, the problem told us to do this two different ways. And again, part of this example is to help us exercise the meaning of the position vector R that we're interested in. So part A says measure the position vector R from point O to point A. All right, so look at what I've drawn here. I've drawn a position vector that starts at point O and its head extends to point A. That's what I'm being asked to use for part A. Part B is saying measure the position vector from point O to point B right here, okay? And guess what? We should get the same moment for both of these parts. Remember, when you're calculating a moment using Cartesian vector notation, what is this position vector R? What is it? How do we define it? Well, remember, the position vector R, let's write this down, R is defined as what? The position vector from the point of interest, which in this case is O, to any point along the line of action of that Cartesian force F, okay? And so what that's telling us is really to calculate this moment, we can use a position vector from O to A or O to B. And that's what this example is helping us exercise and practice, is using either one of those position vectors. So now in practicality or on an exam, you probably want to use the position vector that is the most easiest to deal with, but you could use a position vector measured to any point along the line of action of the force. So let's go ahead and see how this plays out. Let's do part A first. The moment about point O is going to be equal to the position vector OA from O to A, cross product with that Cartesian force vector that we just developed. Now, how do we evaluate a cross product? Well, this basically is accomplished by evaluating a 3x3 determinant. Now, we have another video on that hopefully you can use to refresh yourself on 3x3 determinants. So to perform this particular cross product, the first row of that 3x3 determinant are these unit vectors I, J, K. The second row is going to be the components of R. So I can say Rx, Ry, Rz. And then the third row are the components of F, Fx, Fy, Fz. Okay? And that's what that's going to come out to be. Now, how do we evaluate a 3x3 determinant? Well, we recopy those first two columns off to the side like this, okay? And then we perform some diagonal cross products. So remember, we do this cross product here, this cross product, or double multiplication product, I guess you could say it like that. And then we do something similar going up and to the right. Do these double multiplications up and to the right. And then we negate whatever is up here, okay? And then we add these two values together, okay? So again, if you're a little rusty on cross product or 3x3 determinants, take a look at previous video to help you refresh yourself on that. So for this particular part of this problem, we're going to say MO equals, and I'm going to open up this 3x3, I, J, K. I'm going to have 2 feet, 3 feet, and 0 feet. That's ROA. How do I know that? What's ROA? Well, again, that's the distance from O to A right here. So this is ROA. All right, and how do we get a position vector? We say coordinates of the second point minus the first point. Well, the first point's just the origin, so that's just going to be 2, 3, 0 for the components of OA, right? Now, what are the components of the force vector? Well, we just got that a few steps ago, right? So that's going to be the negative 4.455 and negative 22. Oh, let me color coordinate a little bit better here. I think I'm using black here. There we go. Negative 4.455 and then negative 22.25 and then 44.55. Okay, and then I'm going to bracket this off or put that, boundary symbol there, and then I'm going to go ahead and repeat these two columns, 2, 3 feet, negative 4.455, and negative 22.25, okay? And so what do I do now? Well, this is where I do those cross multiplications, okay? Or diagonal multiplications here. We notice we got a 0 in here, so that'll make some things clear out pretty nicely. And then we multiply up here. We got a 0 in there that'll multiply things out nicely. So here's what I want you to do. I want you to pause the video, and I want you to use this as an opportunity to practice doing this computation, okay? And see if you get the same thing as me. So I'm going to go ahead and write down the answer. So pause the video if you want to do this by yourself. But I get the moment about point O as a Cartesian vector is 134I minus 89.1J minus 31.1K. And of course, this is a moment, so it's going to collectively have units of pound feet. Okay, so again, pause the video and show some work here. There's really a couple of lines of work where you perform these multiplications and add things accordingly. And remember, you're multiplying things down diagonally to get a number here, and then you're multiplying things up diagonally to get a number up here that you then negate, and then you add these two numbers together. When you add these numbers together, you're adding like terms. Remember, you're going to have an I, a J, and a K that come out in this multiplication, and M is still coming out as a Cartesian vector. Okay, so that's M. That's the moment about point O as a Cartesian vector. What about part B, where we were asked to use a different position vector? So this will be the moment about point O equals the position vector OB crossed with F. Okay, now similarly, when I set this up, I'm going to set it up the same way with the cross product, except this time I'm using a position vector measured from O to B. Okay, so if I go back to my original figure, what is that going to look like? Well, this is going to be a position vector from O to B. So I'll call this ROB. All right, now how do I establish that position vector? Well, O is just the origin, so coordinates of B minus 0, 0, 0. So the position vector ROB is literally just going to be 1.8, 2, and 2, all positive values, okay? So if I were to set this up in a cross product or determinant fashion, what's it going to look like? Moment about O equals, and remember I always start that top row off with I, J, K, and then the second row is always the coordinates of R, so 1.8 feet, 2 feet, 2 feet, and then the third row is the value of or the components of of the force. So negative 4.455, negative 22.25, and 44.55, okay? And we're gonna close that off, and then what do? We repeat those first two columns, the I and the J columns, 1.8 feet, 2 feet, negative 4.455, negative 22.25. And then what do we do here? Again, we perform those diagonal multiplications. We've got an I component there. We've got a J component there. We've got a K component here. Then we multiply diagonally up, and we negate everything that we multiply up. We got a K component, an I component, and a J component. And we add all of these terms together, again, negating the diagonal multiplication up here, okay? Putting a negative in front of that. So here's another opportunity. Pause the video and perform this calculation. Gather those like terms, gather the I component terms, the J component terms, and the K component terms, and make sure you get what I'm about to write down. Moment about O equals, spoiler alert, same thing, 134I minus 89.1J minus 31.1K, collectively with units of pound-feet. Now, if when you punch this through, if you got very slightly different digits as me, that would be due to round-off error. So, for example, if you got like 133.7 for the I component, or you got negative 88.9 for the J component, or you got negative 31.2 for the K component, that's okay. That's due to round off error, but theoretically, these are the exact same, okay? Now, are we done? Pretty much. If the problem wanted you to find the magnitude of this, if you wanted to find the magnitude of that moment about point O, what do? You use the Pythagorean theorem, right? And you compute that magnitude by saying, let's extend this out, 134 pound-feet squared plus negative 89.1 pound-feet quantity squared plus negative 31.1 pound-feet quantity squared, and square root all of that. And if you compute this magnitude, again, use this as an opportunity, pause the video, make sure you get the same thing as me. I get 164 pound-feet as my magnitude of that Cartesian moment vector about point O. So that concludes this example. If you found this helpful, please hit like and subscribe, and please be on the lookout for other content like this. Thanks for watching.